Let us start with the lecture number 5 of this course on engineering mechanics. In this lecture, we are going to learn a new quantity. That quantity is the angular velocity of a rigid body with respect to another rigid body. The angular velocity of a body with another rigid body is defined in this manner. It is the rate at which the orientation of the RB changes as observed by an observer fixed to another RB. Now in this definition, RB, a rigid body, can be thought of as a reference frame as well. So we can as well say that we are talking about the angular velocity of a frame with respect to another frame. The frame and rigid body, these can be used interchangeably, and still the quantity that we are trying to describe now remains the same. Thus I have written here rate at which orientation of an RB or a frame changes as observed by an observer fixed to another RB or another frame. The SI unit of this quantity is going to be radians per second, and we will use this symbol omega m bar f to denote this quantity in our course. Now note that the subscript package that we have put with omega has 3 characters. The first character is this is the first character, this is the second character, and this is the third character. The second character is just a bar and it will remain there. It will be the same whenever we write angular velocity for any body with respect to another body. Whereas these two characters are denoting that indeed I am talking about angular velocity of m with respect to f. Let's have a look at the diagram that I have drawn here on the right hand side of the screen to get a better understanding, at least a qualitative understanding of what is meant by angular velocity. So I have put this reference frame F, and to this reference frame we have a frame embedded triad of unit vectors. So E1, E2 and E3 are embedded in F. They all are unit vectors mutually perpendicular embedded in frame F. Now let's consider a body M shown here. To this body I attach a set of mutually perpendicular unit vectors. Those unit vectors are small e1, small e2 and small e3, and say they are attached at a point which is fixed in the body itself, M itself. So small e1, small e2 and small e3 are M embedded. Let's assume that at this current time instant, which is t, the 3 unit vectors which are embedded in M are completely aligned with the 3 unit vectors which are embedded in the F frame. That's what I am trying to write. I'm trying to express here. Small e1 is parallel to big E1, small e2 is parallel to big E2, and small e3 is parallel to big E3 at this time instant. However, when this observer looks at the body, observes the body M at the next time instant at t plus delta t, things have changed. First, the body point C itself has moved, displaced, gotten displaced from its original location, which was here, to here. Further, the orientation of 3 unit vectors which are embedded in the body are no more parallel to the big E1, big E2 and big E3 unit vectors. In general, these unit vectors will get misaligned relative to the big E1, big E2 and big E3 unit vectors. This is a visualization of what can be called as the change in orientation of the body M with respect to F. Since in general the small E1, E2, E3 are no more aligned to big E1, E2, E3, we would say that the relative orientation of M has changed with respect to F. The angular velocity vector tries to measure the rate at which this orientation changes with time. In a little while, we will look at the precise definition of the angular velocity vector. However, I hope that the visualization presented on this slide gives us some idea what physics we are trying to capture, what physics of the kinematic aspects of the body we are trying to capture by this vector omega mf. On this slide, I have presented a few more examples to consolidate our idea, consolidate our understanding of the situations in which this omega mf vector, the angular velocity vector of m with respect to f, in which case it will be 0 and in which case it will not be 0. At least this much understanding we want to extract using this slide. Again, in a little while I will give the precise definition of omega mf, but with this slide I want to encourage ourselves to be able to think in which case the angular velocity vector will be 0 and in which case it will not be 0. Now if it is not equal to 0, the next question would be how much it is. If something is not equal to 0, then the next obvious question is to measure exactly how much it is, how different it is from 0. That part we will address when we go to the next slide. For the time being, we have to only judge whether omega mf is 0 or not 0 in various scenarios that I have included here. In this case, let's focus on the first case. Here I am showing a reference frame F with E1 and E2 as big E1 and big E2 as the F fixed unit vectors, and E3 is coming out of the plane of the screen. Now this observer here is observing an aircraft, which is our body M. He observes the aircraft at two time instants, at t and at t plus delta t. I have drawn two unit vectors here, small e1 and small e2, and they are body fixed. They are fixed to M. And again, E3, small E3 unit vector is coming out of the screen of, coming out of the plane of the screen. Again at time t, small e1 and small e2 are perfectly aligned with big E1 and big E2. But at a later time instant, what happens, the point C moves in a straight line, straight horizontal line, as observed by our man here. Even though C has moved, E1 and E2 remain parallel to big E1 and big E2, even at the next time instance. Now, based on the definition that I gave on the previous slide, I pose this question: whether omega mf is 0 or not equal to 0. I just expect this much of an answer: 0 or not 0. Since E1 and E2 continue to be perfectly aligned with big E1 and big E2, the answer here is omega mf is indeed 0 for the body M as with respect to body F. Let's move to the second case. Same reference frame F, same body M. At time t, small e1, small e2 perfectly aligned with big E1 and big E2. However, at the next time instant, C has moved here. So C seems to be following a curvilinear path for itself. Still, the pilot of this aircraft had managed to keep E1 and E2 parallel to big E1 and big E2 as observed by the observer fixed to frame F. I pose the same question: omega mf is 0 or not equal to 0. Clearly, E1, E2 have not changed their orientation relative to big E1, E2, big E1 and big E2, and thus omega mf is still 0. This is the correct answer. Let's have a look at the third scenario. Same aircraft, same reference frame F. Here, the point C has moved along a horizontal straight line as observed by the F fixed observer, but the orientation of E1 and E2 are no more, the orientation of small E1, E2 are no more the same as big E1, big E2. And thus, in this case, the angular velocity of the aircraft with respect to F must not be 0. It is non-zero. Fourth case, the point C seems to be following a curvilinear path. E1 and E2 seem to have changed their orientation compared to big E1 and big E2. So this is the direction of big E1, this is the direction of big E2. So as observed from this reference frame F, small e1 and small e2 have changed their orientation, and thus in this case also omega mf is not equal to 0. We go to the next case, case 5. Same frame, same aircraft. At time t, the orientation of small e1, small e2 are shown in red color. They are perfectly aligned with big E1 and big E2. However, this time the aircraft is a special aircraft in the sense that this point C continues to remain at the same place where it was at time t. So at both time instants, the location of C does not change as observed by our observer on frame F. However, at time t plus delta t, the orientation of small e1 and small e2 are shown in blue color, and thus in this case also the conclusion will be that omega mf is not equal to 0. So I hope with these different scenarios it is clear, at least qualitatively it is clear in how to judge whether omega mf is 0 or not equal to 0. Now we will move to the question of how we exactly quantify omega mf. If omega mf is not equal to 0, how much it should be? Let's address this question now. What is the precise mathematical definition of omega mf? We have a sense of the physical understanding by now, and we now want to quantify. All right. So let's now focus on a body M, which is shown in with green color as the body outline. The body outline is shown in green color. It's a rigid body, body M, and it is being observed by our friend fixed to F. And for reference, our friend in F has put 3 unit vectors, body fixed unit vectors, and he is observing what is happening to body M. Now inside this body M, we have identified a small cube, a material cube on the body. That material cube is shown in red color here, and I have labeled 4 of its vertices. 4 of its vertices have been labeled A, B, C and D. Now at time t, this cube is oriented in a manner such that the unit vector small e1 is along AB, the unit vector small e2 is along AC, and the unit vector small e3 is along AD. Small e1, small e2 and small e3 are body fixed. They are always pointing, e1 is always pointing from A to B, small e2 is always pointing from A to C, and similarly small e3 will always be pointing from the material point A to material point T. At time t, we have this alignment, but at a later time, at t plus delta t, this cube will undergo a motion such that these three small unit vectors, these three unit vectors denoted by small e1, small e2 and small e3 get misaligned relative to the directions of e1, e2 and e3. To highlight this disorientation, relative disorientation in a more clear way, I have redrawn the directions of E1, big E1, big E2 and big E3 on this diagram. After all, these are unit vectors, so I can displace them and put the tails of these unit vectors at any point I want. As long as their directions remain the same, we are fine. Now, in general, when this cube undergoes disorientation, we want to quantify the level of disorientation using certain small angles. What are those small angles? Let's focus on this part of the slide. On this part, I have shown three planes. What are those planes? Here I am showing the plane of A, E1, big E1 and big E2, which would be this plane. Right? Plane containing A, big E1 and big E2. On this plane, we are identifying the projection of point P at time t plus delta t. So all these pictures that I have drawn on the right side of the slide in green color, they are at time instant t plus delta t. So B must be, in general, B will be out of the plane of A, E1 and E2. B itself will be out of the plane. However, we can take the projection of B on this plane. I am calling that point where I get the projection of point B as B triple prime. Once I identify the projection of B on this plane, I connect B triple prime with A. I get a straight line and I denote this angle as delta alpha 3. So delta alpha 3 is the small increment, is a small angle that B triple prime is making with the even direction. Similarly, if I look at the plane of A, E2 and E3, A, E2 and E3, which is shown here, I am identifying the projection of point C on this plane, and that projection is C prime. And then I connect C prime to A and I measure this small angle that this line AC prime is making with the E2 axis. I call that delta alpha 1. Finally, I go to the plane of A, E1 and E3 shown here, and on this plane I try to identify the projection of point D at this current time instant, and I call that projected point as D double prime. I connect A to D double prime and then I call this small angle as delta alpha 2. Delta alpha 2 is the angle A D double prime is making with the E3 direction. All these descriptions I have included here also. With these three angles now defined, identified geometrically, now I am in a position to write the precise mathematical definition of the angular velocity of body M with respect to F as what I have here in green color. So omega mf is a vector, and I am expressing that vector using the 3 unit vectors fixed to frame F. So there are 3 components of this vector, and the 3 scalar components are rates of change in the 3 angles that I identified on this part of the slide in the limit delta t going to 0. So the first component of omega mf is limiting value of delta alpha 1 by delta t with delta t going to 0. The second component is limiting value of delta alpha 2 by delta t, and the third component is delta alpha 3 by delta t in the limit delta t going to 0. This is the precise mathematical definition. This is how we measure the rate at which orientation of M is changing. Orientation of M is changing with respect to an observer that is fixed to frame F. The definition that I gave and the description of the angles that I presented, these are true for any general motion that the body may be performing with respect to frame F. General 3-dimensional motion that the body M may be performing with respect to body F. In the special case, there is a special case in which the body may be performing, body M may be undergoing a planar motion with respect to body F. What do we call a planar motion? The motion, M is said to be performing a planar motion with respect to F. Body M is performing a planar motion with respect to body F if every point of RBM is confined to a plane. Every point of RB moves in a given plane, and all such planes are parallel to each other. If body M is performing a motion of that type, we say that M is having a planar motion with respect to it. Now it turns out that in the case of planar motion, the definition of angular velocity and its visualization as rate of change of some angles is substantially simplified, and that is what I want to show on the next slide. Suppose that the planar motion of the body M is such that all such planes of motion which I mentioned here are perpendicular to E3, big E3. Without any loss of generality, I am assuming that the planar motion is such that all planes in which the particles of body M move, they are all parallel, they are all perpendicular to the E3 axis. And then we will see how the definition of omega mf simplifies substantially. So in the case of planar motion, what will happen that this point B will always continue to be in the plane of A, E1 and E2. Similarly, point C will also remain always in the plane of A, E1 and E2. Since point B will always remain in the plane of A, E1 and E2, the projection B triple prime that we talked about earlier will be nothing but B itself. B triple prime is coinciding with B. And C prime will be non-existent. C prime will be non-existent. Right? Because C prime is supposed to be the projection of C in the plane of A, E2 and E3. But C is always in the case of planar motion, C is always confined to the plane of A, E1, E2 itself, and thus C prime will not even exist. So delta alpha 1 remains 0 all the time. That's what I have written here. Similarly, in the case of planar motion, the point D will always remain on the AE3 axis itself, or the axis passing through A and parallel to E3. That axis will always retain D on itself, which in other words mean D double prime will be non-existent, and which leads to the conclusion that delta alpha 2 will also be 0, will remain 0 at all times. And in that case, omega mf of the body is simply the limiting value of delta alpha 3 by delta t, and this scalar component is along E3 itself. Even there is no scalar component of omega mf in E1 direction or E2 direction. In the case of planar motion, suppose the body is AB itself and it is undergoing a planar motion in the plane of A, E1, E2. In this case, omega mf can be written as the rate of change of theta along, the magnitude, the scalar part of omega mf. The scalar part of omega mf will be rate of change of theta with respect to time, and the direction of the vector will be along E3. But here this angle theta can be finite. So in the case of planar motion, the scalar component of angular velocity can be obtained by differentiating, finding the rate of change of this finite angle itself. However, in the case of general three-dimensional motion, when omega mf when body M is not undergoing a planar motion, the three components of the angular velocity vector can be obtained as rate of change of small changes in the orientation of small e1, small e2, small e3 relative to big E1, big E2 and big E3. Now let's go back to the general three-dimensional motion of M with respect to F. Same diagram what I had a couple of slides ago. And here I want to mention that following the definition of omega mf that I showed a couple of slides ago, we can prove that the rate of change of small e1 with respect to f, the rate of change of small e1 the rate of change of the small e1 vector, body fixed e1 vector, can be expressed as the cross product between the angular velocity vector and e1 itself. Similarly, the rate of change of e2 with respect to f can be written as the cross product between the angular velocity and the e2 vector, and similarly for the third small e3 vector, the rate of change with respect to f can be expressed in this manner. These three relationships can be derived using the definition of angular velocity that I mentioned earlier. This derivation is not a part of this video. However, as I mentioned earlier, each of three relationships can be proved. We are going to use these relationships now onwards in our other derivations as well. Now, if these three relationships are true, we can prove that this relationship will hold good. What is this relationship? If A is a vector fixed to M, if A is a vector which is fixed to M means in other words, A is a vector such that for this observer who is tied to M, neither the magnitude nor the direction of this vector changes. If A is such a vector, we can show that the rate of change of the same vector observed by this man here can be expressed in terms of the angular velocity of this body with respect to this. And the precise relationship is here. Is the cross product between the angular velocity of the body and that vector A which is fixed to M. We can prove it. This proof I am going to present here. The proof starts here. Let me first express A using small e1, small e2, small e3. In other words, I am expressing A in this coordinate system. This is a frame fixed Cartesian coordinate system. This will be the representation. Now, if this vector is fixed in M, in that case, these three scalar components must be constants. Only then our M fixed observer will not see any change in the vector. Okay, so this assumption leads us to this conclusion that these three scalar components must not be changing with time. We will use this relationship. We will use this realization in a little while to conclude this. So I write A in terms of small e1, small e2, small e3, and then I try to find the derivative of A with respect to F. So I hit the right hand side with this operator. Applying product rule of differentiation, I get 6 terms. These 6 terms. And then these three terms which are appearing here, they all involve rate of change of one of the unit vectors, one of the unit vectors tied to the body. On the previous slide, I told you that based on the definition of omega mf, we can prove that dE1 dt with respect to f can be written as omega mf cross E1. Similarly, dE2 dTf can be written as omega mf cross E2, and dE3 dt can be written as omega mf cross E3. So we get rid of these time derivative expressions, or we get rid of these time derivative operators here by utilizing this property of omega mf. On the other hand, we have this type of terms. However, these will be individually zero. Why? Because A is a vector fixed in M. So these time derivatives of the scalars must be zero. So what we are led to, this equation leads us here that rate of change of vector A with respect to F must only be the sum of these three terms here, which I have written here. And then I take out omega mf cross part of this expression, and I let A1, A2 and A3 go inside the parenthesis such that I get back the A vector. I get back the A vector here. So I have combined these. Omega mf is a common factor. We then realize that this is nothing but the A vector itself, and thus we are led to the conclusion that rate of change of A with respect to F is omega mf cross A. In this proof, I have used an M-fixed Cartesian coordinate system, right? When I expressed A vector in terms of small e1, small e2, small e3. However, the final relationship that we have obtained here is coordinate system independent. So to prove this equation, we have taken help from an M-fixed coordinate system, but the final relationship is coordinate system independent in the sense that this equation will hold good whatever your working coordinate system is. If your working coordinate system is a path coordinate system, this can still be utilized. This equation will still hold. If it is cylindrical polar coordinate system, this equation will still hold. It's good to keep this in mind.